Hi guys, welcome to Astronomy. I'm going to take you through some basic ideas of astronomy right now, and let's see what we got. When you go outside at night and you take a look up at the sky, it looks like a dome over the planet. And if you think about the planet being a sphere, the dome then is a larger sphere that the planet is within. So we would call that the celestial sphere. And any object in space would be called a celestial object. So that would be the sun, moon, stars, or any object in the sky. A satellite would be a celestial object. An airplane, however, no, that's not a celestial object. That's within our atmosphere. So that wouldn't be a celestial object. We are always moving, which means the celestial sphere is always moving. But we understand it's the spin of the Earth. So the spin of the Earth is causing all the celestial objects to appear to rise in the east and set in the west. Now, why do they rise in the east? Well, that's the way we're turning. We're heading directly east. And that makes everything else appear to come up in the east. Don't get fooled with this. If you go to the southern hemisphere, which way are things rising in the southern hemisphere? Well, are they also heading to the east? Of course. So everything would appear there also to rise in the east. So what objects does that include? The sun, certainly. The moon, How about all the stars? Well, we're turning that way. So the reason the sun and the moon come up that way is also the reason the stars come up that way. All celestial objects appear to rise in the east. You can see immediately why airplanes aren't included, because they can cross the sky from any direction. So if we turn one complete turn in a day, 24 hours, that's 360 degrees. In 24 hours, when you do the division, that's 15 degrees turning every hour. So everything in the sky would appear to move over us at 15 degrees per hour. All right, nice and easy. 15 degrees per hour. I'll show you a little bit later how you can measure it with your hands. All objects appear to circle Polaris. Now, why is that so? Well, let's say so there would be Polaris right there, all right? So all the objects would be apparently going around Polaris. That's why, because the Earth's north pole is pointing directly at Polaris on a line going through our axis. That line intersects very neatly with the star Polaris. Now, Polaris is not by any means the brightest star in the sky, but it's the North Star. It's right over the North Pole. Decently bright star for that point in the sky. And so we see it holding stationary while all the stars appear to circle it. The farther the star is from it, the bigger a circle it would make. If you have a star way down here, it's going to be making a huge circle around Polaris. Okay. We have two motions we have to think about. One is our daily motion. In one day, we rotate on our axis one time. All right, so that's rotation, turning of the Earth on its axis in 24 hours. Causes a unit of time we call a day. But we also are going around the sun. So the movement of the Earth around the sun in 365 days, it causes a unit of time we call a year. All right. So it is the Earth's motion that causes time to be. So if we have a view of what the sun's paths are in our sky through the year, it would look like this. And when we take a look at that in December, look at the path we make. We rise 23.5 degrees south of east. So we rise in the southern sky. Notice all noontime suns are always in the southern sky. So if we're rising south of east and we're getting into the southern sky and then setting south of west, we don't have far to go. So we don't have the sun up for that many hours in the sky because it's still moving 15 degrees per hour. So that would be what the sun's path is on December 21st. Notice, it doesn't get very high in the sky, and it doesn't stay up very long. That's why we have winter. because when the sun is down there, we're not getting much heat from it. We're still losing a lot of heat from the Earth, so we're always losing more heat than we're gaining for a couple months after that as well, so we fall into wintertime. 3 months later, we're at March 21st. We rise due east, we set due west. So the sun then, it's up for a longer period of time, it's up higher. So we get considerably more insolation. The Earth begins to warm. Finally, when you get to June 21st, the sun is up the maximum amount it can be. It takes a long time to get there. Why? Well, now we're rising 23.5 degrees north of east. We're setting 23.5 degrees north of west. And that means the sun has a huge path to take as it moves through the sky. So the sun is up for a very long time. Again, 15 degrees per hour. That's going to make for a much longer day and a much warmer day because the sun is up for so long. Now the sun remains up not quite that far, but close to that far for, well, until September 21st. So the Earth continues to warm for a long time after that June 21st date. So let's talk about planets for a minute. The word planet means wanderer, from planetos. It means wanderer because they move against the background stars in the sky. So, like everything else in the sky, in a single night they move at 15 degrees per hour because of the Earth's spin. But they also very slowly change position against the background stars. Now, planets are tiny compared to the sun, and they're in orbit around the sun because of the sun's gravity pulls them around. Now, all planets appear to move every night a little bit further to the east in our sky. Every night a little further to the east. But when we pass them in our orbit, they can seem for a little while to be moving backwards. That's a really hard one to explain in the geocentric model, in the Earth-centered model. That one was a crazy idea to explain. But in the heliocentric model, it's very simple because it just means we're passing the planet. If you are driving on a highway and you pass another car, before you pass it, that car is moving like everything else is moving on the highway. But when you pass it for just a moment, the car appears like it's moving backwards. Same exact thing with planets. All right, so let's talk about constellations. Right? Constellations are just a pattern of stars in the sky. They're usually associated with legends and myths of ancient cultures. Those myths, those legends, they tell you nothing, and I mean nothing about the sky. Many astronomers have no interest in the legends and myths, and as an astronomy person, I also share that. If you're studying the myths and legends, you're not studying the sky at all. You're studying people. You're studying anthropology. You're studying how people came to decide that these myths and legends are represented by the stars in the sky. But of course, the stars in the sky, they're far away from us. They have nothing to do with us. So some of the constellations that are well known are Orion the Hunter and Taurus the Bull, Lyra the Harp. They just seem like shapes in the sky. So we make up stories to go with them. The reason we use constellations are just, it's a map. We can divide up the sky. We use 88 constellations to divide up the sky into regions so we could say, hey, there was a supernova in Taurus. And astronomers will know somewhere in that region of the sky, there's probably a distant galaxy that had a supernova occur. So it's not that it had anything to do with the stars that we use to make up the constellation Taurus. It's just that region of the sky. Right, so some of the constellations we use, at least our culture has inherited. These would be some of the major constellations, and they're fun to learn. They're interesting to learn. You have an idea of where to look for things if something is going on, if there's a comet going through, and they say if you look in the right-hand quadrant of Gemini, you'll see a faint fuzzy ball, and that's the local comet. Okay, you know where to look in the sky. What really advanced humans greatly is learning the models of the night sky. Now, you don't have to think too hard to know that Earth is standing still. Everything is moving around us. I don't feel any motion. Do you feel any motion? Even though we're actually moving 700 miles an hour towards the east, I don't feel it. It doesn't seem obvious to me that we're moving at that speed. So it took modern science, or really developed modern science, to understand how wrong we were when we thought Earth was the center of everything. That was called geocentric, and we really did think Earth was the center of everything. Everything seems like it moves over us. We thought we were very special, so everything seemed reasonable to move over us. But of course, science has helped us understand our position in the universe. So that's what we used to think. Right there in the center, right there in the center was the Earth, and everything moved around us. But that made it really hard to understand, especially when the planets seemed to back up. So we came eventually to understand the heliocentric model. The heliocentric model means that all the planets move around the sun. Doesn't mean that everything moves around the sun, because the sun is just one of billions of stars in our galaxy. Certainly, it's not the whole galaxy moving around our sun. Our sun is moving around the galaxy. So, but the heliocentric means that all the planets are going around the sun. That makes sense. So we have rotation on our axis, and we have revolution around the sun, and that all takes place within the heliocentric model. Helio means the sun, and heliocentric means sun. Right? So we have certain apparent motions of the sun. Our system of time is based on how the sun appears to move through the sky. So an apparent solar day is the time from sunrise to sunset. Apparent solar noon is the time when the sun is highest in the sky. Okay, it's not ever overhead in New York State, but it appears highest in the sky at apparent solar noon. The year is how long it takes the sun to return to the same place in the sky. You mark out where the sun is in some particular group of stars, and how long it takes the sun to get back there, that is a year. So all of these units of time aren't based on the sun's motions, really. They're based on the Earth's motion. So we have a number of days that we mark out, and these are approximate: December 21st, June 21st, September and March 21st, 21st, 22nd, 23rd, depending on the year. But just take a look at this. When we're tipped in position 1, if you mark out where the sun is directly overhead, somewhere in the northern hemisphere. If you look at position 3, where is the sun directly overhead? Well, it's somewhere in the southern hemisphere. If you look at position 4, which you can see clearly, the sun is directly overhead somewhere in, oh, look at that, somewhere right on the equator. All right, and it would be on the equator as well in position 2. So this causes the seasons. All right. So the Earth revolves around the sun, tilted on its axis by 23.5 degrees. This is what's all right. June 21st, the summer solstice. Look at where the sun is directly overhead at the Tropic of Cancer. Okay, notice how Tropic of Cancer, 23.5 degrees north, that's not very far from where New York State would be. So the sun is quite high in our sky. All right, we get a lot of hours of daylight. Look above the Arctic Circle. Everywhere above the Arctic Circle has daylight no matter which way you turn. Look at the Antarctic Circle. Everywhere down there has darkness no matter where you turn. Notice that the sun is quite a distance away from the Tropic of Capricorn. Okay. So June 21st, summer solstice. Summer solstice is when the Earth's northern axis points most towards the sun. Sun is overhead at 23.5 degrees north, Tropic of Cancer. At the North Pole, the sun appears to move around the sky in a complete circle. Maximum height is 23.5 degrees. December 21st, look where the sun is directly overhead. Now it's Tropic of Capricorn. So Now think about where New York State is compared to that. We're a long way from the Tropic of Capricorn. That means the sun is all of that distance away from being directly overhead in the sky. So that explains why the sun is very low in the sky on December 21st, the winter solstice. Again, look at the Antarctic Circle. You see the sun is up all day long. Look at the Arctic Circle. You see that no matter which way you turn on that day, you get no sun. Right? So December 21st, winter solstice, 3 months after equinox, the Earth's northern axis is pointed away from the sun. Winter solstice. The sun is at 23.5 degrees south. So if we look at this, we see the winter solstice, December 21st. Look at March 22nd, and these all vary in dates, but approximately March 22nd. Now the sun is directly overhead at the equator. Okay, June 21st, now we're pointing directly towards the sun. September 23rd, again, we're pointing straight. So September 21st, we call it the autumnal equinox. That's right after the summer solstice, 3 months. The sun is overhead at the equator. At both poles, the sun moves in a circle on the horizon. Everywhere has a day 12 hours long. The sun rises due west. March 21st, the vernal equinox. 3 months after the winter solstice, the sun is overhead at the equator again. We want to measure movements in the sky. We have a handy tool. Your fist, held out at arm's length, measures almost perfectly 10 degrees. Everybody's fist. A finger turned on its side is about a single degree. So if you look at the sun in the sky, and use the number of fists to figure out how many degrees it has to move before it hits the sunset point, divide that by 15, and that is how many hours till sunset. So if you get 3 fists till the sun hits the sunset point, that's 30 degrees. Divide by 15, you got 2 hours. It's about 2 hours till sunset. So if you're outside, you can always, even without a watch, you can have some good idea of how long it'll be. Right? So a fist, about 10 degrees. A hand, widely spanned, is about 20 degrees, if that's useful. So the Foucault pendulum. This is a way of proving that the Earth is actually spinning on its axis, right? Remember, we had a lot of trouble ever figuring out that the Earth was moving at all. The Foucault pendulum proves it in a really cool way. It's a long pendulum. It's set moving back and forth. Now, the thing about this is, as long as no other forces act on the pendulum, its plane of motion will not change. It'll just go back and forth. But it does appear to change. And that is simply because the Earth is actually turning. Pretty cool. So this is a Foucault pendulum in a museum. So if you walk into the museum and you see how it's tilting, look very closely at the lines it's going through then. As you're leaving the museum, you'll go past this again. A few hours will have passed, and you'll see this moving in a different plane. No, it's not. It's moving in exactly the same plane as it started, but the museum has turned underneath it. Right? That's the idea of the Foucault pendulum. So if it was at the North Pole, it would go through one complete rotation in a day, and it would be back to the plane. Now, notice that if it does 180 degrees, it seems like it's back in the same plane again as well. So a few hours.